Welcome, ladies and gentlemen. Jag är Etlene Anne. Jag är Onri Jay Benally. So, I was able to actually update the channel. I I uploaded some video footage talking about the updates and what's coming in the future for this channel. I also talked about, of course, the podcast. Not my podcast, Barrington James' podcast. So, yeah, that's on there. Well, I'll mention some of those things later. But there's something I did not mention in that video, which was a bit more on the side of tutorials. So there are tutorials of this open source program called KLayout, right? And KLayout is just a name for the program. It's used to design chips, classical chips as we call them, and quantum chips. So both of these chips, the design components, like the individual devices or lines or whatever artistic structure that you feel like drawing, you can put it on there. In fact, I encourage the public and also learners to explore the artistic side of nanotechnology in the chip design, because the quantum chip design, these nanoscale features that you draw onto the chips, they might seem really technical up front, but if you think of it in an artistic sense, then you can create for yourself a reference that you can use in the long term to understand how to take advantage of the design features or design tools in the programs. So KLayout is one of them, and it's really good. There's another one that we call LinkCAD, which is also able to perform a GDS file output that you can use to upload to a lithography machine. Lithography that's used for fabricating nanochips and quantum chips and so forth. Whether if it's laser based, or if it's based off of an electron beam, or if it's based off of some projection system or immersed projection system, or nano imprinting machine, or scanning thermal probe of some sort to achieve these features, there still needs to be an aspect of how to understand the layers. Like, how do you take advantage of the layer in the design file? It's like one layer to the next. You might have one single device on a single layer of the chip, but the thing is, the size can be split up into further layers themselves. So even if your chip only has a single layer, you can split it up into, I guess you can guess you would say it, you categorize it into different sizes. So if I'm going to pattern this feature that's like 2 nanometers or 10 nanometers, I'm going to group those together more or less. And if I'm going to pattern something that's like, let's say 500 nanometers all the way up to like maybe 5 microns, I'm going to group those together more or less. In fact, I could probably create a spot size that is slightly smaller than 500 nanometers, and then reduce the spot size for those other features that are around that make up for the difference between 500 nanometer diameter and the spot size that was made smaller, if that makes sense. A smaller hole, and then in order to make up for the roughness around it, fill up those tiny little arrangements of geometries that will actually fill up and create a complete 500 nanometer structure. See? And then you can start to group the largest structures that are like more than 5 microns. Maybe it might be 100 microns or something. And you want to group those together. So larger features should stay with the one layer. Medium-sized features stay with the another layer. And then the third layer, you might have nanoscale features that are really small, like single digit, close to single digit. Or you might even split it up into four and make all the single digit features together, and then all the double digits and so forth together within a certain range. You can group them into layers. You can have three, four, maybe even five. If you did five, you might do like 1 nanometer feature. If you could do that, and then everything else beyond 1 nanometer, 1 or 2 nanometers, could split it up into other layers for that one device on that one single chip layer. So there's a difference, of course, between design layers and chip layers. The chip layers, it pertains to the actual physical chip. The design layer, however, is only a matter of file organization, if that makes sense. So this is something we can actually kind of help bring to the public as far as the design constraints for quantum chips. Because in the VLSI community, the very large scale integration of chip design, they have their own constraints. It's usually not considering quantum effects and the other quantum constraints. So that's them. They have their own thing going. And for quantum chips, we have our own constraints. It has its own constraints that are considered within Qiskit metal. So Qiskit metal, and you can use Qiskit metal, which is from IBM, the quantum chip design platform, and then export that to K-Layout. And then K-Layout can help you organize those files more easily, and then show you a general layout of the design, and then you can show that to the world. And then from there, take it to the lithography machine, which you can either pattern yourself if you have access to some system like that as a learning method, or perhaps even if you built your own lithography system by chance, and let's say we made a tutorial on YouTube here on this channel on how to create a lithography system from scratch, like an open source project that you can follow from one video to the next, and then show how to use that lithography system program, and then actually carry out your design on there, whether if it's artistically or for scientific purposes. So we could do that. That's what I envision. That's my vision for the future of this channel. We'll talk about those things, but you see, this is not just the design side. This is also the fabrication side. It's hardware, and then we'll eventually talk about how to generate the diffraction rate or diffraction lines that can actually split up light and interfere with light. When you look at it with your naked eye, it'll shimmer all kinds of colors that you would normally see on a butterfly. So there are some butterflies that have like a really nice glittery blue color. So this blue shimmering color from the backs of the butterfly, or some bugs, they have these. When you look at it, it looks like like a gem or something that's built into the shell of the bug. So we can generate those colors more or less by creating stripes that are within a certain distance. For example, it could be 1 micron apart from each other. So we can create a few lines, maybe a group of 5 or 10 lines, and then we can space them apart like 1 micron, or even we can space them apart half a micron, or well, half a micron is 500 nanometers. So at that point, we just transition over to nanometer scale, and then anything smaller than that, we could do like maybe 300 nanometer spacings between the lines, and then these 10 lines, if you fabricate it, you can actually use that and show some really brilliant colors. I don't have the chip on me in my pockets at the moment, but I would show you that. In my pockets, maybe I could show you that later, not right now. But for now, I mean, you could use that as a way to demonstrate the diffraction and also the interference of light. And perhaps even if you want to make your own meta optics at home, then it might be possible to do with such an open source system. So That's what's coming. And in the beginning, I actually will create some useful tutorials on how to perform this the design generation or the source code, the source file, because there are no tutorials on how to create the source file. The source, I keep saying file code, source code, which is a Python file. There's a certain format that it follows. You just follow the format. But the thing is, this is only assumed because apparently people who write some basic tutorials say that if you are coming here with some Python background, then it might be possible. But if something that you're learning in Python to generate those design file of the chip, the quantum chip, then you probably somewhere you learn from somewhere that there is a Python source file for that. But the thing is, I don't know where people learn how to write these source codes, which is why I'm going to bring it here. I'm just going to go ahead and generate those files and then show how to do those things from beginning to end. I think that will be useful for the general quantum community and for the chip design. It'll be good. No problems. So let's see. What else did I not mention? There was something about miscellaneous. Let me look at my list. So I created a list here. My brain is on here. My digitized brain. Let's see. Oh, gifts. I don't think I mentioned gifts on there. I wanted to say something about gifts, but there is a strategic way of using gifts to communicate with the public when you are in the scientific or STEM field. And gifts really save a lot of space. They illustrate the point very well, and it's somewhat automated because you just simply place the GIF on a slide or somewhere, and then the GIF will play over and over again with some amount of quality to it. And it just sort of animates itself like that. It's a wonderful technique, I think. So whatever it is that you have in mind, you can draw it out. You could even place a sequence of images, take pictures with a phone, for example, and then put that image in a sequence and then place it onto a GIF generator. And then the GIF is something you could place on a slide, which is good for those who are general, or I'd say those who are visual learners. Those of us who are not visual learners, still it makes sense because at least you can try to map it into your mind how that thing might exist in reality. So you'll get the context once you finish watching this live stream. If you watch it from beginning to end, you'll get some context on what's being said. So other than that, that's the only update I wanted to add to the other update that's been uploaded. So thank you very much. We'll talk more about quantum hardware soon, and we'll do some other like some fun projects on here. That's the goal. I also want to talk about this one fun project that it's going to be coming up very soon. It's not entirely related to my quantum PhD research, but there's the use of egg whites. So there's documentation. I created some Monte Carlo calculations for that, but it shows and confirms that you can use egg whites together with electron beam lithography to perform a chip design. And it'll be a fun design. Like I said, you use the artistic side to actually learn all the features by itself. It's a lot of fun. Instead of having to do it without art, you probably could, but you'd have to be obsessed about the technology in the first place. So, yeah. And we'll talk about maybe some other things like the thought process in regards to the way I've been able to, not been able to, but the way I evaluate humanity as an indigenous person, because I have a certain way of viewing the world, and it's pretty optimistic, I would say. I'm generally an optimist, but that gives me motivation because I want to learn about the way the human brain thinks, how the brain operates. So I try to write these things down of things that I notice, the way humans behave, the way people behave, the way they respond to things, both historically in books and also in stories that are told orally, and also stories that are told in person as I hear them, of the many thousands of people I've met over the years since my childhood.